All right, welcome everybody. My name is Steve Conrad. For those that haven't met me, I'm associate professor in system engineering, and I kind of a lot of the work that I do is around these four thrusts of investigation. One of them is sort of our water energy nexus research and how do our water and energy systems interact and perform. Another one is using AI for augmenting system engineering. I do a lot of work with human dimensions, but my fourth research thrust is one that I've been working on really for about 20 years in a variety of ways, and that's sort of our sustainability systems and our ecological resilience, and sort of how do we connect, sustainability with with resilience. So today I wanted to sort of share some of my thoughts on how we've been investigating and trying to unify these two different views of resilience. Right? So we have an ecological view of resilience, and then we have this engineering view of resilience, right? So I appreciate everybody here and online just sort of listening to some of my ramblings for the day. But what has inspired some of my research and some of my investigation into resilience, is this impressive built environment we have, right? If we look around, we've managed as, humans to build pretty impressive infrastructure, pretty impressive examples of human engineering, human ingenuity, right? So we, take some examples here in China on your left, right? They're moving 54 trillion liters of water over 1,000 kilometers, and that's pretty impressive, right? So next time somebody says, I'm too lazy to go get a bottle of water from the kitchen, just think back to this and think, wow, we're moving far volumes of water from that. And so this adjustment, and this built environment has a direct impact on the environment, has a direct impact on where we see, right? And so the graph on your right is, is merging trends in global freshwater availability as both climate change and human-induced change affected these water systems, right? And you can see across the globe, these areas of red, these areas of sort of pressure that we've been putting on. And so as we apply pressure, as we, engineer our systems, we're dramatically changing the structures of our system. Right? Another example was back in 2015 when I was doing some work in British Columbia. We promoted run-of-the-river hydros. So these sort of small hydroelectric facilities that we would connect, and take some of the rivers and divert the river, run it through a microhydro. And microhydro was really just defined at that time anything less than like 1 megawatt. So a lot of large dams are much larger than that, so you have gigawatts of power production. But these are sort of small scale. But you can kind of see an example of just a number of applications that were, presented for British Columbia consideration, over 500 applications, saying like, that's great. Lots of people were interested in sort of diverting water from these streams and putting it back. Since then, that's really kind of two things have affected the investment in microhydros. One is significant concerns in terms of how it might change the water temperatures of the salmon fisheries. Even though it's taking the water and putting it back in, some research at the University of British Columbia discovered that it actually changes the chemistry a little bit and causes confusion for salmon when they're trying to run, go upstream. So that chemistry change, was a big factor. But I would say probably the second factor was a change in policy from moving from microhydro to building one big, 5 gigawatt dam. So that's actually what BC Hydro went. So, you can see like in British Columbia, they said, well, let's just build a bigger dam instead of all these little micro hydro dams. And, I think we see that example quite a bit when we think of infrastructure. Build bigger, right? Build much bigger. If we think of resilience and like, well, what if people change? What if we need more water? If we need more treatment? Let's build bigger, right? Let's build bigger, greater capacity. So these are just two examples of this kind of build bigger approach. The one on your left is the Jean Marchand wastewater treatment plant in Montreal. So it's the third largest wastewater treatment plant in the world, and it treats water from about 10 million households. Right, so all that water goes through the centralized system. And then on the power production side, the Three Gorges Dam is the largest, hydroelectric facility, that's there, with 112, terawatts of hours of power, right? So pretty significant annual production, which is, put it back into homes, about 11 million homes, right? So that big structure. But in my research, what I found with some colleagues of mine is that these centralized systems and trying to build out and meet the needs of society through the centralized systems is pretty limited. So the graph that you see here is some investigation we looked at. What if we were to take and follow this conventional approach, to meeting the needs of wastewater services for cities around the world and build them out in the capacity that humans typically build things. So Brian can tell you, you get an idea to build something and then decades go by or something like that. So the same thing sort of approaches where we think about building wastewater treatment plants, right? So this graph, if you look at this kind of small little black line in the very bottom, that's the highest build rate ever recorded by the World Bank in terms of how fast they can build infrastructure. So that little black line. And then the blue lines are what the rates of production, rates of growth that are actually needed to meet, the needs of cities around the world, right? And so this need is exponentially greater than what the current solution that we have. And so it just means we really kind of think about different approaches to doing this, different ways that we look at infrastructure, different ways we look at this built environment. And that's sort of like, interconnected with some of my work on resiliency and saying, well, one of the goals for building this infrastructure is to create more resilient communities, more resilient, systems. This conventional approach may not work for us, right? So then, where should we focus instead of the central big approach? Where should we focus our efforts on resilience, for sustainable system engineering, right? So lots of questions around, sustainable system engineering and resiliency, for example, like how do we design systems so that they can inherently be resilient to disruptions? Or, what strategies really kind of influence resiliency and sustainability together? Things like, so you've already seen some examples of human interventions and how these interventions affect the natural and built environment. And then, the vast majority of us here are engineers. All engineers, raise your hand. Okay, like two of us do this, right? So how do we, what are the engineering frameworks on resiliency that we can think about and apply, especially when we're trying, with risk sustainability, right? And then you have these kind of core functions that I look at in my research, which is like, should we engineer systems to maintain or function? Should we engineer systems to adapt? Or what about just getting it right the first time, right? Really focus on really good time. And so a number of these efforts around, engineering sustainable systems is kind of focused on, minimizing the impacts that we might have, or resisting change to sudden disruptions, adapting to, to sudden or chronic external changes, or really looking at ways that we can transform our system, right? So, just kind of some of the basis for looking at how do we kind of reconcile a number of different views are, two different directions we see resiliency sit in one. So in one area, we see a lot of resilience efforts focus on this resistance and prevention focus, and a lot of it we see kind of on this adaptation focus. So I want to kind of explore those two differences in more detail. So first, let's do a little story of history. We'll go back in time and just sort of look at like where did this concept of resilience come from? Has anybody heard resilience in the news recently, or resilience in proposals or anything like that? A couple of people have raised their hands. A few people have. Yeah, so right, it feels like resilience is all around. It's like the structure of a number of things. But we kind of go back and we say, where did this idea of resilience come from? So this is just some work from a former PhD student of mine from the University of British Columbia when we were doing some work on resilient frameworks. And we sort of say like, well, it goes back into both engineering and ecological frameworks, but also social frameworks. So back in the 1960s, we can think of the societal kind of viewpoint of resilience, go from the Latin word, regenerative, which is the kind of bounce back, right? So bouncing back from that. And so around the 1960s, 1970s, the idea of like safety engineering really became a big focus, in terms of things like that. If you ever really fascinated about engineering frameworks and principles, safety was not part of some of the earliest engineering principles. So cost was typically one of the guiding frameworks for engineering. And then safety started coming into play, along the same sort of realm as Silent Spring and environmental revolution. And so engineering, resilience started to say like, well, we're not only trying to build things, but we want to think about like how these things are safe, right? And so they're like, what's the robustness of these systems? In the 1970s, a big push on ecological frameworks, especially after a number of ecological disasters and in those particular areas. And so Buzz Pauling, which I'll talk about in a second, introduced the idea of ecological resilience, which is this ability of systems to absorb. Now we're moving into the 1980s. We had, the Rio Conference. So now we're looking at the 1987, the Sustainability with Our Common Future, introduced these frameworks around resilience and sustainability science, right? Which says resilience is not only a feature of the system, but also a social system, right? So how do we engineer systems and build things, create things so that they also utilize resources for future generations, right? So we're starting to provide that. So we're combining those in the 2000s to social ecological resilience, right? So along this same sort of framework of resilience in my own personal journey, in the 80s, I remember my first climate change seminar I attended to. So some guy came in and said, "Hey, I want to talk to you about global warming." I'm like, that's cool. What's that? Right. So I went to this and they started showing me these graphs, and he said, "Well, it's heating up." I was like, "Well, that doesn't sound so good." And so that kind of stuck with me as someone in my early 20s and just sort of thinking about this. I finished up my degrees in optical engineering and cognitive psychology. I was very interested in people. I got interested in how we use lasers to monitor particulates in the environment, and that really just those two driving forces, shared and created my interest in this framework around resiliency and environmental systems. Right. So now we're moving to 2000s now. We made it through the millennium, right? 2000. Anybody back with their computers? Probably only a few of us in the room that have computers. But they're like, "Oh no, I'm gonna make sure secure that resilience." 2000 gonna turn over. Right, so we made it through there pretty good. The resiliency is sort of moving forward into the vernacular. Things like community resilience. Engineering instead of just infrastructure and safety engineering. Like, how do we actually build capacity in our systems? Looking about infrastructure resiliency, right? And so a whole slew of frameworks are now coming out. They're trying to say, like, what exactly is resiliency? I would like to say that was helpful, but in many ways, it really created even more, a little bit of a convoluted space. And that's what I've been exploring with all these frameworks around what exactly is resilience, right? And so at the same time, I got my master's in environmental technology management, international sustainability, started leading the sustainability services and consulting, doing a whole bunch of sustainability work, in those 2000s, late 2000s. Then I got connected with a really interesting part of my life. I worked for a sustainability strategy company, which included sustainability marketing. Now that was very fascinating. It was all about like, how do you sell a product, and then how do you do that? And then my job was to say, don't do that. In fact, your products aren't environmentally friendly and not sustainable. So I only had the job for a year. You can imagine that really good connection. But from there, I said, I really like this idea. I actually started my own consulting group, Resilience Consulting Group, and sort of focused on really working through there. Got my PhD, resource environmental management, and so this kind of from this mid 2000s to now, I've been really working a lot of things on kind of like defining what exactly is resiliency. Focused kind of in the water sector is my main frame. But I wanted to go back and sort of share kind of what has grounded some of my research and where I'm trying to understand these commonalities as well as differences between our ecological systems and our engineered systems is this viewpoint from one of the really great Canadian ecologists, Buzz Pauling. So sort of the father of ecological resilience theory and ecological economics, right? So Buzz Pauling had this framework with a number of his colleagues with Gunderson to push this idea of panarchy system, right? So if we look at a system, our systems aren't linear. They really move through these ever evolving aspects of growth, stability, and we see stability in the system, and then something happens, and we have this massive crisis, and then hopefully from there the system is going to be resilient. We'll get something novel out of that crisis, and that crisis will then generate some exploitation, and we'll have growth again, right? So we see this as sort of a panarchy cycle. Hopefully, if you have a significant other, you can manage your relationship that way. So if you have like collapse, something novel, and go through that. All right, and so these hierarchy cycles, basically these adaptive cycles, represent a variety of like human systems and environmental systems, and so we can learn. Engineering can learn first from some of the successes in nature that we see from these panarchy cycles, right? So one really great example of lessons from a panarchy cycle is forest succession, right? And so in forest, we have a barren landscape, and we see some seeding, we see some intermediate species that start to grow, some fast forest growers, and then some taller, trees will take over and they create this climax community, right? And then so something happens, perturbation fire, not uncommon in Colorado. And so that's not really the end of that community. With the exception of some really intense fires, somebody will probably break and say, that's not true, Steve. You have a really hot fire, you can cause ecological collapse. But let's say we'll have normal fires and such thing. And we go through that, right? So that really what you see is a crisis stage. And so we can learn that nature has a substantial lead in trying to develop and manage these systems through the succession, right? And so we kind of explore this. So, what's happening in this cycle. So after that, that fire, goes back, we might start to see grasses and perennials start to grow again. And then we go through this growth cycle, and we have woody pioneers, and then we come right back to that climax, right? And so it's reorganizing itself. So forest reorganizes itself, and it doesn't actually collapse. So that's a nice sort of framework that we can explore how resilient is our particular systems. Like, how are they following this panarchy cycle, or are they exhibiting linear structures, or are they actually adapting and moving through that, right? So kind of in some work by a colleague of mine from the University of Queensland has explored water supply investments, right? And so we looked at this analogy between water supply investments and what we see in resiliency and ecological systems, right? So over on your left, you can see two different types of ecological systems that have experienced a disturbance, right? And our high resilience system, where it'll maintain system function, go through adaptive cycles, you can map out, where it is in the cycle. And you can sort of say, like, it's just moving all around in this vegetative cycle. Versus the non-resilient system, you start to see every disturbance, you'll see a loss of system function. So essentially less than, or in this case, it was vegetation cover. So you have less and less function, right? And so we don't really want to see that in our engineered systems. We'd rather see, systems adapt and respond through that. And so over on your right, this graph is showing some investments of cities in water efficiency after their millennial drought. And so what you want to see is that, a decrease in water efficiency, but also a decrease, in per capita energy use. And if you look over there to Perth, we actually have the wrong direction occurring. So they're making great investments in reducing the amount of water that's needed for individuals, creating essentially more structural resilience to water drought. But they put pressure on their energy systems, right? So they're really kind of going off in the wrong direction. Or you can see like Sydney and Brisbane are moving through this adaptation, right? So you can see maybe a little bit of increase in energy intensity, but then they adapt and they come back. So they're all trying to move through that particular structure, right? So that ecological framework helps us to say, like, just sort of like, our systems, are they adapting or are they moving towards a collapse, right? So as engineers, we probably understand, these exploitation and growth phases, right? We like to build things, like to grow things. That makes perfectly good sense, right? Here's some resources to build something. Give you a kit, boom, I'll build it. I can do that, right? So that makes a lot of sense to us. We can go through that. But even conservation phases of this panarchy cycle works pretty well. If I can put out this efficiency curve graph here, so probably be like, oh, can I get that? Yeah, I'm trying to do this input-output. We want to make sure it's with efficiency. We want to maximize the output, minimize our inputs. So it's essentially a conservation phase, right, that we go through. But what I found is what's troubling for engineers is, this collapse stage. That doesn't sound so good, right? So, you build something, you design something, why would you want that system to collapse? Why would you want it to, be destructive in that aspect? And so we struggle a little bit with the 3B space. So at system engineering, we like to promote growth, incentivize novelty, to develop something new. We're researching new ways to do that. How many are you researching ways to break stuff? Oh, Jeremy, sorry, Jeremy's figured out ways to break stuff. Yeah, that's a good point with the cycle challenge. I'm trying to break it. Hopefully you're trying to figure out how to reorganize and adapt after that. But we're kind of struggle, so the efforts we put in, we're flood prevention, right? We're doing that. Or we build government subsidies to maintain that stability, right? If you see a system trying to collapse and adapt, we might actually, put subsidies out there. And generally, there's hostile policies against that kind of change, right? And so it's a good thing. So, and some work with a colleague of mine, Lucy Rodina, at Environment Canada, we sort of looked at, okay, where is this perspective of engineering resilience and resilience in sort of the academic literature with that, right? And so, it's not untrue that you hear this word resilience more. And so if you just look at the literature to 2017, when Lucy published her paper here and we gave a presentation at this workshop around resilience, yeah, there's definitely an exponential growth in understanding that resilience, right? And so resilience in our water sector that I work a lot in is kind of loosely defined around these concepts of improving water security, so really building some of those safety aspects, but also reducing vulnerability. And so security and vulnerability. Now, before I kind of go more, I wanted to just share these sort of pictorial views of resilience. If you haven't, taken a resilience class or things like that, I think these are really nice pictorial views of different perspectives of resilience. So in you have this engineering perspective, maintaining some of the factors I just mentioned, in terms of both security and vulnerability, right? And so engineered resilience, when we increase security, we're sort of trying to, I don't want to call it honeypot, I'm trying to think of Jeremy's term you might use, but essentially, we're looking at resilience and we're building a system of structure so that system can move all around, right? But it's going to maintain its resilience. And if you have really steep walls, you have a high engineered resilience because that wall should come right back down, right? And so that's we think that's the big. In the panarchy viewpoint, our ecological resilience is more or less focused on creating less desirable states, right? And so, as perturbations occur, you might get that ball pushed in a particular direction, but it'll be pushed over into a new state, as long as that's like a stable state. And so you're really kind of moving to that stable state. And then we sort of add in our so-called ecological resilience structures. And when we think of our system societies and ecologically, we start to accept that there's many less desirable states, but there's also many more desirable states, right? So you can have multiple states that the system can be in, right? So now you're thinking, now we're sort of thinking about engineering. So you have to design a system with that kind of viewpoint in mind, so that there's multiple states that the system could be in, except that one particular state. So structurally, it's a little challenging because if you were designing or engineering a system, with, trying to make those walls really steep, you're avoiding or ignoring some of those other states the system can be in. Okay, so that's sort of my view. But let's take a look more at the literature. So some of the types of definitions that we see around resilience is maintain reliability, cope or transform. That absorb a shock with that. But we do start to see kind of in that social systems realm, like community, the cope or adapt, right? This kind of concepts of coping and adapting with that. So recognition that maybe in our engineer systems, we like to build something and they stay there, but our societal systems or human systems, they can figure out how to adapt. Now, if anybody's ever done work on humans, you probably would think it's easier to adapt the engineer systems than they get the human system to adapt. But that's the point. So here, system engineering, our international committee sort of on system engineering has a resilience working group. And so we looked at this and said, well, what do we think it is, right? And so I love to say it's kind of an ecological system, but it's really, really kind of an engineered system, right? You get in a bunch of engineers together, and that's what we're going to think about. And so our focus is this idea of fundamental objectives to avoid, avoiding, withstanding, and recovering, right, from that adverse event. And so that's that engineered resilience, right? So engineering, resistance and recovery, ecological, release and organization. Equilibrium is a big thing. One point of equilibrium versus ecological systems, multiple points of equilibrium. We think of engineering, we think of these perturbations as threats to the design. Whereas in ecological resilience framework, you would think of those perturbations as opportunities for growth, opportunities for your organization. So those changes mean just there. And the conditions are stability, some near the equilibrium, where in ecological systems, we more or less think of resiliency and stability based on the structure itself. That structure is what's resilient, not necessarily a single, equilibrium. So there's really kind of this vague difference between vulnerability and resiliency. A lot of the literature has been on resiliency, has been focused on this capacity to return to the original state. And then vulnerability has been defined as this weaknesses and fragility, how, like, in that state, right? So you're creating and you're addressing vulnerability, whereas resiliency is in that. So, they're really not the same, right? So sometimes we think of vulnerability and address vulnerability, create resiliency, but we're not really doing that, right? And so, then, other kind of findings from Lucy's work, I kind of already mentioned this, but if we think of, the viewpoints of the natural system, having redundancy, and our general system properties and adaptation. Okay. So what we have is, and this is kind of what I've been trying to understand, is how to reconcile these differences. We really have these two potentially, conflicting viewpoints on resiliency, right? So we have this non-adaptive view of resiliency, where, we think of normal operations down there on the right there. We have normal operations, and adverse event occurs. We want to detect that adverse, what's happening, it's a faulty operation. And then we have a response, how to respond to that. We've got to mitigate that. Because we're mitigating that, maybe we have a degraded mode operation that goes through, and then we fix it and goes that way. If anybody's ever had something that goes into limp mode, you know what limp mode means? It's like a base default programming mode when they don't know what's happening, right? So everything fails down, goes in limp mode for a while, some control programs use quite a bit, and then you fix it and you put it back up, right? So this non-adaptive view of, first let's prevent it from even happening, but if it does happen, we'll just go into this, minimum function view, and then we'll fix it and move on. So that's a very different view than ecological systems. And so in my water sector, I see that view implemented quite a bit, right? So this is an example of a dike construction. So if you're managing, floods, sea walls, we might build a dike, right? And so this part of British Columbia is updating dike management plan, and we said, let's get some climate scenarios. We'll go through, we'll figure out what our dynamic models will be, and we'll figure out where dike failures are going to be, right? To models, and then we'll say, like, okay, how big of a dike do? Right? And so that's really what the probably could save a few thousands of dollars and just be like double the size of your dike was the response to this whole particular aspect, right? But it was sort of like the view that was had from the engineering community was building that structure. But an alternative viewpoint, well, actually before that, just say, so this graph here on the top was sort of like another illustration of, even recent paper in 2023, following that design approach, following that structure of like, well, how do we build that, and then if we're going to add in risk and probability, well, we'll just add that top and we'll just build a bigger dike. And so this then the question becomes, how big of a dike do we need to manage a 2100 sea level rise? Well, an ecosystem adaptation, instead, alternative approach here was in this problem here, sort of how natural processes contribute to flood protection, was an adaptive approach. So rather than just having water come in and overflow, why don't we actually build in an ecological system in the front? We'll build in some weirs, some sedimentation. We'll actually absorb that water. We'll manage that inflow of water, and we'll sort of work through that so that the storms So, building in that adaptive capacity versus bigger types is the kind of the difference approach. All right. So we have sort of looking at this vision, share some of my research here, visioning resilient water systems and working with sort of Sydney Water. They did a really great job of putting together kind of these scenarios for water utilities out to 2040. And two scenarios they looked at were, scenario building better together, right? And so creating adaptive driven structure where communities and industries work together. And then we have autonomous communities, which is really great, where you sort of say like, well, maybe we have instead of centralized, we go through the distributed. So example of build better together might mean cleaner technologies, smart technologies, integrated, commercial use with residential use, green infrastructure. We can get around that, right? That sounds pretty cool. That's all engineering stuff. I can build clean technology. I can build this kind of cool stuff like that, and move into that. Or alternative future, which would be, well, maybe what we need is more like decentralized communities, and which are like technology by the community, and where we have water supply and resources are driven by local solutions, and extreme weather measures are addressed at the community scale instead of a centralized scale, right? And so two different types of visions and approach. And one you might say is kind of more the engineering resilience, one more the ecological resilience. So we said, well, let's vision that with the group of water utilities. So I'm not going to go through all of this. I just wanted to sort of share some of the messages that we got. So we conducted, this would be like 4 workshops now, because we also did one here in Colorado with industry. So a couple hundred industry individuals come together and sort of say, like, how do we define resiliency on this? And basically these ideas of coordination, so that sort of interlinkages, responsibilities, in connection with private industries, some aspects on the management. Lots of conversation around creating flexibility and natural systems, connection with natural systems, upgrading water treatment plants, not based on demand, but based on, this adjusted and appropriate investment, right? So those kind of adding in flexibility. And then also comments on this idea of, improving faster than extreme, right? So there's still some engineering there that sort of response rate, but also some areas with that social ecological perspective with public acceptance. So we kind of just mapped that out into the elements of resiliency, so the elements with lots of infrastructure issues, technology, data availability, supply sources, and organization, all demonstrate that resistance perspective of resiliency. But the more broader kind of adaptation was organization, funding models, supply sources, research, urgency, right? So looking for adaptation. So we repeated this conference here in the Rocky Mountain to try and say, like, well, how does it differ from, maybe the U.S. perspective? So this was a lot of these were Canadian utilities that there. So we had a workshop, same thing. And so we defined water resiliency was defined by the participants that it would use advanced technology, strengthen interpersonal connections, and work within frameworks that allow adaptability and dynamics, right? So I think here in our Rocky Mountain states, we're trying to think about that adaptation. All right, so how do these two kind of relate back to the sustainable system engineering? Well, we can think of, different priorities for sustainability and resilience. Who's heard of sustainability? No, nobody's shaking heads. Do I need to go through a lecture on sustainability? Okay, let's go back to 1972 again. You want me to do that? Okay, so we can prioritize desired outcomes, right? And that's sustainability. So it's sort of prioritizing those outcomes, like future generations, quality of life, environmental, and it focuses on these end goal objectives. Whereas resiliency, it focuses on maintaining processes to withstand disturbances, and also kind of focus on prioritizing this functionality, this adaptability. All right, so it doesn't have an outcome in mind. So we need to start to connect those a little bit. So researchers have proposed a number of different views on this. I want to kind of share my view. A number of researchers say that resilience and sustainability are separate objectives, right? And so we can track resilience separately when we can track sustainability, right? So I might describe resiliency and sustainability completely separate. nothing contributes to each other. Separations in programs can focus on independent elements, right? So things like building codes, policy regulations, and economics would promote sustainability, and resiliency would be earthquake retrofits. Now, I think it's a little bit obtuse in its viewpoint, but we did sort of examine this, right? So Anya looked at this response if we're sort of looking at this disconnected viewpoint of resiliency, right? So this graph here is sort of looking at what would happen if we had kind of like a non-adaptive stage. It's like, so we're really trying to maintain that system resiliency, right? So you can look at system performance on your y-axis and time, right? And so if we would go through and we put in some hardening efforts, we do some things that would improve the engineering resiliency of it. So you might harden the pipes, so to manage pressure, or expand the capacity of the supply source, right? And build that bigger treatment plant. And so the idea being that disturbance that occurs would be completely absorbed in the system, right? So that you have kind of like this fail-safe perspective where we're trying to do that, that redundancy, maybe some redundancy would do that, but then it would be followed through this absorption phase. So kind of really following through that. But my view on kind of sustainability and resiliency is that they're really kind of interconnected with each other. And so you improve resiliency, you improve sustainability, right? So on your left there, we can sort of look at the viewpoint of sustainability and how a resilient system might affect that function. And so, sustainability, so you have a disturbance, right? So a resilient system would absorb that quickly and bring it back. So therefore, a resilient system would enable that to be more sustainable. Whereas less resilient or anti-resilient might see losses in that sustainability structure. And then on the other side, right, once you create resiliency, or once you create sustainability, that critical functions are also help with that resilience efforts, right? So if you have economic disturbance, a highly resilient economy will come back, and what that'll do is create more function. Whereas you have an unsustainable system, you start to see collapses in one part of the economy and part of the environment, things like that. That's in part in sort of impact your resiliency. So a different view on how those things would come together is like if we had a resilient response within our urban system. So this graph here is another example of sort of like, well, what's sort of happening within that system when you have these disrupted systems, right? So if you're sort of moving through and you have that fail-safe point, right? So this fail-safe point here is that sort of sudden disruption, and then your system starts to respond. If that fail-safe threshold is crossed, the productive adaptive capacity would then come into play, right? And so it would determine the performance of that system, that fail-safe portion of the system. So imagine going back to that limp mode. If you had a major failure in the system, instead of that small little limp mode being basic function, you actually had all this adaptive capacity that could come in and say, okay, yes, the primary direction is failing, but now we're going to increase that adaptive capacity rate. And so the amount of that adaptive capacity sort of shown in red there is that you assess and measure how much of that capacity based upon the types of disturbance. Okay, so coming back to sort of applying that to cities, work a lot in little cities, and we sort of been talking about that growth cycle, this ability to withstand disturbances, but what about that collapse phase, right? And if we were to, we really don't want cities to collapse, right? That's generally not so positive. You kind of want cities to go just sort of skip over that collapse and say we're going to go right back to that knob, we're going to go right back to that regrowth phase, right? And so if all-out collapse in cities are to be avoided, really what we have to think about is like how do we then release and reconstruct the function when we're at that point of conservation and its disturbances are potentially creating the risk that those systems may want to collapse and right? And so been working a little bit on this idea of regenerative frameworks for resilient city functions. So instead of having city function being like a single point, so transportation's goal is to get people from A to B as fast as they can. What if transportation's function was to provide resources and services for the other part of the city, right? And move through those. What if energy and water are interconnected? What if all this function, right? So it's focusing on adaptive and interconnected processes where the release stage is a planned reconstruction and a planned reorganization of the system, right? And so you go through and planning that. So then you learn to manage those creative destruction so that undesirable things occur, or they do not occur, right? And so this will get really deep. Some system science stuff I want to pull out here just for a second, and then I'll show you a pretty picture. Just to cleanse your palate. But, so if we kind of combine a couple different viewpoints, right? So on your far left there, you got that ecological framework of panarchy. And so this panarchy system has this constant evolving, right? And if we try to stretch that out into a dimensional framework, we can see what's really happening is you're moving to a different system, right? So you're moving through it and you're moving through and organizing into a new system, right? So we're moving through that. And so we're actually shifting the function of a system. And so in the middle there, we can envision that what if, so right now cities are sort of a real centralized function. We have this, big treatment plants, we have, highways, we have this centralized function, and they're independently connected, right? So we have this current structure, and that we're kind of trying to follow the panarchy of the collapses. There's an accident on I-25, and the highway backs up for 2.5 hours, right? That's the right? So if we reorganize and start to interconnect functions, we can move that distribution and the organization of the city from the centralized system at the bottom to a regenerative system at the top, where you have an interconnected system of supporting function, and that supporting function creates regeneration. So this can't happen immediately, otherwise that would be devastating, but sort of move and think about it, right? And then your graph on the right, which is, sort of think of these individual functions moving through sustainable development and eventually creating ecosystems. So where's my pretty picture promise? Okay, so an example of that sort of concept is how could we support regeneration and creative destruction? So does anybody remember what happened in 2020? Yeah, does. Well, that and also a lot of people left cities. So in fact, more people in America left their cities than the other sort of European countries, right? And so what we see is we have this kind of domestic movers moving out of cities, moving out of this regular structure. And sort of so we see this shift and movement to the suburbs, right? So reshifting where people are, and also reshifting how cities are functioning. And one of the sort of downfalls of that shifting function are abandoned buildings, and especially commercial buildings. So a lot of commercial buildings. San Francisco has a real sort of problem there with many commercial buildings that have been abandoned as people have shifted out into that structure. So the easiest thing would be like, well, let's just go ahead and use commercial buildings as a residential area. The challenge with that is commercial buildings are built differently than residential. So they don't have the same sort of, heating and cooling functions. They don't have the same code functions. They're not really ever been built for that, right? And so you can obviously do it. You just have to come in there. You have to reorganize and restructure that. But that's challenging. And it's not very cost affordable. So what if you instead designed your building with this idea of the panarchy cycle? What if you said instead, we're going to create a building that will naturally look to absorb those shifting cycles, right? And here might be the shifting cycles of our society, where we have people who are moving downtown, to work, and moving out, or people are maybe moving downtown to live. So in Vancouver, Canada, that was actually a shift that we saw. We had people moved out, and then a whole bunch of people moved into the downtown city. So most of downtown Vancouver is residential and very few commercial, right? And so they did it the old-fashioned way. They just built commercial buildings. But let's say you decided instead. And so this stack in Melbourne, Australia, is an example of sort of designing for that creative collapse, the creative aspect, right? And so it's hard to see here on the graph there, but if you look at the stack Melbourne, you can get a lot of pretty pictures of their design. But the idea is you have these neighborhoods and these independent functions of how that building would perform with support for both commercial, retail, and living space. And that can be reorganized and restructured quickly. And so moving through that, right? And then adding in some of the ecological systems. So it's just kind of a nice example of designing for that adaptive function, right? So as we sort of think about where we can reconcile, this need to create a engineered system that's resilient because it can absorb these shocks. That engineering perspective, this building can do that because as the economy shifts or other things will do that, it can absorb that. And then the adaptive structure from the ecological system that says it needs to reorganize itself and create a whole new system structure. Right. So that's what I have for you. Thank you very much. I'd be happy to take questions, get a little conversation going about where you think resilience should be, and I'll write down some stuff. But anyway, thank you very much. So questions or thoughts?
Yeah, I think you kind of touched on it a little bit in your figures, but could you go into more detail on the difference between like acute shocks to the system versus long-term trends to like kind of the operational environment?
Yeah, something like the fire versus global warming, right? So both of those would still be a perturbation, for the original design. Like, so if you engineered a system that was expecting to cool a building at a certain, rate, and then you got, that global warming would cause that perturbation, so that the systems that are in there are going to be overtaxed eventually, right? So then you have to go in and replace it or rebuild the building or redesign it. So that's still, we really kind of still consider that as that collapse function, that perturbation. But the main function is really kind of that rate, right? So the rate and how quickly. So if you're evaluating the resiliency of the system, you want to evaluate the response for both of those functions. Can it absorb something like a fire, or is it more absorbing those slow trend lines?
So I'm thinking that most water utilities build climate resilience in their operations by building more tanks or finding more water sources, right? But could you mention another strategies to build climate resilience rather than creating more infrastructure?
Yeah, so like in the water sector, we're trying to create water, or climate resilient water, so to speak. You're right, it's one of the biggest strategies, right? Securing new water supplies, right? So Thornton, Colorado, over 20 years ago, thought of this mostly for growth. It's thought about like, well, how do they secure more water supply because they're seeing that growth, that long-term sort of like global, like warming population growth there. So then they secured water in northern Fort Collins, right? And so now they're building a big pipe that will take water from the agricultural fields. I think it's actually out of the river, and then take it all the way down to Thornton, right? So that I'm not a big fan of that, things, but that's kind of like the typical example. You're right. Water utilities will focus down on that, or they'll focus on the demand side, which is sort of like tell everybody to take lunch hours. A more adaptive structure would be using like on-site water recovery, right? Pushing that supply and those sources out to the demand points instead of having to be centralized. So rainwater capture, for example, regenerative gardens, for example, that would treat the water, on-site treatment, those types of things would be an example of trying to take more of the adaptive. So then you're moving that pressure from the central point of the system and you're pushing it out into the system. Devin, did you have a question?
I was just wondering, like, how, like I see things occur, like Asheville, North Carolina, or something, right? And it gets wiped out, and then it just comes in and it just like rebuilds what it used to have, right? And so this is like a mindset, and you need to have the infrastructure to that mindset, right? And like, how much is this getting built up to have this? Because the infrastructure right now is like, let's just build like it used to build, right? Yeah. And it's like only little novel things like, oh, we have this one building in Australia, right? Or we have this one building here. But then you see other buildings that like Notre Dame, just build it like it used to be because we want to preserve the history, right? Let's not do one of these other cool designs that appeared in the New York Times, right? So like, do you feel like this change in publications is really starting to result in the type of infrastructure that can go in after, say, one of these disasters and say, hey, this is the time to do it differently. Because, you know, like the fire in California, they're probably just gonna go in and build and sell to rich people again, right?
You know what's driving? Yeah, no, I agree. I mean,
And is that
It's-
like
it's
insurance
always-
driven even?
you know, if you look at just the economic costs, often it's less expensive to just build back or to build something new than it is to invest in that, right? But I think one of the biggest drivers which will push that change outside of government. You know, so I'll go back to Australia. So Australian government as a whole decided that that was wrong, right? So if you experienced a flood and your house was taken out by the flood, you had to build back your house with flood resiliency in it, right? So examples of that, you know, you go into Australia and kind of look around, you might find houses where they have floodable basements, right? You know, in those structures. So they're moving that around so that they can absorb that, right? So that's like a government approach. But actually, I think the insurance agencies are going to be a big driver for pushing building differently or creating different systems, right? Because they're the biggest payouts against those kind of disturbances, right? So, you know, either it'll be from like higher premiums, or it could be mandated efforts that you might have to take in order to even get insured, right? And so I know a few of us in this room have had examples of like insurance companies, you know, saying you have to mitigate that, otherwise we're not going to do it, right? So more and more fires, Colorado's facing people who are like challenged to insure their homes, you know, so I could see that. So I see the insurance company actually being one of the major, or insurance industry being a driver for that. But yeah, it does need a little driver. We almost have to take that panarchy and put it as a social system, because it's still kind of linear and it's like burned down and we're like, oh, just move that point back to point A and we'll just do it again, right? Versus restructuring that. Yeah, I don't know if that's positive. But yeah, we all have to pay really high up. That's kind of our scene. Any questions online?
I have one question.
Yeah.
Thank you for the presentation. I might be thinking worst case scenario here, but with these systems, like you mentioned, humans are messy. And the big factor with humans being in a system like this is their convenience. And when you have a system like this that's kind of adapts when there's a problem or something, it's adds an inconvenience to the humans involved in that system. How do we account for that?
The convenience factor.
Yes.
You know, I mean, I don't know fully. I have my personal thoughts around it. You know, I believe that like if I was to live in a stack building, for example, things would be more convenient for me, and you would experience that. You know, so moving to a resilient system, you're hopefully addressing and creating more convenience for yourself because you're not having to struggle through those problems, right? So if you have a highly resilient home to flood, everybody floods, and you like have to like drain your basement. So that sounds pretty convenient to me. But I think it's more communicating that message, to the decision makers, that how adaptive resilient systems are actually more convenient and create more opportunities. But I don't have anything on that. Good point.
So thinking about convenience, I'm thinking of your graph that had the plans on it that started out spread out, centralized, and then came together toward the end. And it almost seems like at one end, got the traditional high monarchist way of governance, centralizing the organizing of the cities, all of that. And then on the other end, you have almost this like new, like libertarian way of living, where you're like more independent. You don't necessarily need the bottom half if the top half is working, as long as the bottom half comes along eventually, And so thinking about convenience it almost seems like the more the bottom part fails, the more the top part seems relevant to people. And in a way, that's like its own kind of resilience, because you would hope that there'd be a connection eventually, but you need both, right? So I kind of like that. Think that politically would be an interesting way to describe like support for a pluralistic way of living that is also connected.
Yeah, I never thought of that perspective, but yeah, as you're creating almost like more self-autonomy, that might be considered more libertarian views, in terms of that governance, because you're now, as an individual, if I had on-site water treatment, I had on-site power production, I had on-site services. Now I'm, governing that part of the structure. The one aspect though that could challenge the libertarian views, I don't know much about that, but it's like interconnected, right? And so if we really push that whole resilient framework, we'd even want the, your power production to be connected with your neighbor's power production, right? So then you're providing power to the system as well, right? And so now you become a bigger viewpoint. So you're managing your power production, but you're also sharing your power production, right? And you're managing your site, but you're also connected and connected with the rest of the system. You haven't figured out what that government structure looks like, but I'm gonna
It'll figure itself out.
figure itself out. Yeah. Okay, good. Was this new for anybody? Just curious in terms of, yeah, about these things. Good, good. Find it interesting. Any feedback?
Kind of curious what your kind of initial framework was for this. Like, it seems like you can take this and apply it to many scenarios and many levels. Like you mentioned the building in here, right? So this has a very slow moving heating and cooling loop. We have rapid changes here, and it never keeps up, right? So that's a perturbation, but like, is it a failure? Where you draw the line to say this is a failure, right? Like, well, it's not plus or minus X of what the set point was. It's a failure.
Yeah.
Well, like we're all fine. Put a hat on, you're good, right? And then like in a broader context, when stuff starts becoming more interrelated and there's lots of external forces, like it seems a little bit murkier and less clear cut, right? And like, so like, I was just kind of thinking like, what would an example be like? Thing with North Carolina was brought up, like, okay, we don't have running water, we don't have sewage, that's clearly a failure.
Yeah.
Like, but it's not maybe, how do you judge that too? It's a failure for N people that were in the epicenter where basically this major washout happened, but everybody else was fine. So we succeeded, right? You see what I mean? Yeah, like how do you, I mean, like you have to place realistic boundaries on this. And I was just wondering if like, there's like any kind of real world concrete examples of like, here's kind of the framework, here's how we sort of evaluated it. And if we judge it by this, maybe it's just some, like, is there any, like, has this been applied and like demonstrated or anything?
For sure, yeah. Yeah, so that's kind of like, I didn't go into that work here, but like, how do you then measure resilience, right? Which is sort of like, and even answering simple questions like, how many pumps do I need to be resilient? Or how many distributed power systems do I need to connect to each other to be resilient, right? And how fast should a system respond to be still considered resilient, right? And so that I didn't present that because there's almost as many views on measuring resilience as there are perspectives of resilience, right? So we have like sort of the graph theory view, which is like mapping out those interconnections, and we sort of say like where those failure points go, and then we map out that structure, and you think lots of interconnections that could be resilient. Then you have sort of a time response function, which we could apply to this building, for example. We could say like, if we're trying to maintain 20 degrees Celsius or 68 Fahrenheit, and you get that, whatever happens from Wyoming, but I've been out here a couple of times and it's like 40 degrees cold, and the building, drops and it takes a while to restore, right? So that time function we can apply. And then, then it becomes like a stakeholder perspective, which is like, you can measure that function. From a resiliency perspective, it recovers. Just like a forest recovers, it might take 15 years or 20 years for a forest to recover, or even 100 years. So that system is considered resilient, but not if you're necessarily living in that time frame, right? So that scale and temporal components have to come into play as part of that measure. But yeah, if you're interested, I can send the whole PDF and slew of measurement structures too. Hey, yeah, it's fun stuff. Okay, well, I think if any questions online or anything else, I think we're at time. I appreciate you giving us your time, and thanks very much for your conversation feedback.